Welcome back, everyone. Enormous pleasure. Take down, you can try it at the hour.
Here. So it's a pleasure to be here in Bristol. I haven't spent a lot of time in Bristol before, so nice to be here with you guys. So my point is going to be that whatever theory one might have about observer, relativity of measurements, or all the rest of it, at the emergent levels of thermodynamics and biology, there must be an experience of the passage of time and of the arrow of time. And a lot has been written about thermodynamics. In a sense, slightly new will be I'm going to emphasize biology, because I think this is crucial in this, that at this level, biology actually constrains physics. Now, there's a tendency from a lot of our physics colleagues to say at the fundamental level, there is no arrow of time, and there is no passage of time because we believe in the Wheeler-DeWitt equation or whatever. My standpoint is going to be that all very well, but you've got to take into account in this room at this moment where we do experience the passage of time. That in your theory, you better come back. New theory. I will discuss how this can fit into a suitable space-time view in an emerging block universe where the future is not uniquely fixed by the past because of quantum uncertainty, and I will make some comments on how this relates to the emergence of brains that experience the passage of time. And this is fully compatible with general relativity. So I'm not, and the thing about general relativity, which I will emphasize, general relativity basically is telling you you've got a space-time picture. It says you've got differential equations of a certain type. It does not specify what the boundaries of that space-time are. And that's the issue. What are the boundaries of the space-time in which general relativity is to be applied? And then I will finally say that I remain puzzled as to how all that I say relates to the scale invariance view, which is this. Okay, taking time seriously, things actually happen in time, and there's this macro-micro tension. Particularly, you've got reversible laws at the micro level, Hamiltonian dynamics, and some people say very emphatically that the only thing that occurs at the micro level is Hamiltonian dynamics. But you've got irreversibility at the macro level, and you've got the second law of thermodynamics there. This is an absolutely fundamental feature of the macro world of physics, chemistry and biology, and also physics. And Roger Penrose, for instance, writing about this, talks about breaking a glass. You've got a glass on the floor, it smashes, the bits scatter, the shards of glass. In principle, is a viable solution of the shards of glass. Reverse the direction of time, and that never happens. And actually there are some questions about whether that is even possible for that to happen, which we could think about. And then the processes of life are very much a one-way kind of process. Developmental processes, you start off a zygote, your cells grow, you start off as one cell, you end up as 10 to the 23 cells, and then the whole process comes to an end, a one-way process, never. So in the real world, the past and future are not predictable from the present. That's another thing I will be emphasizing as well. And the dynamics of the real world, at the classical level, is simply not Hamiltonian. And I can illustrate that. This glass of water, if I ask you what's going to happen to this water, you can't tell me, because that has happened to Hamiltonian. Okay. Yeah.
Absolutely. It might be, but not at any level that we could verify. I mean, I understand the point clearly, but are we absolutely sure that if we were not a God that could see every precise detail?
Okay. Well, I think let me comment on uncertainty and then ask me that question again. In a sense, what you are saying is, from my viewpoint, what you're saying is that you don't believe quantum measurement processes take place, whereas I do believe they take place. So
Even within classical mechanics, it's not correct because the instabilities that apply to dynamics like this are such that you have to know every part of the universe, including the ones in your own head doing the calculation, because you know it won't do your own calculation. Even the electron, the observed within the universe, you don't know what it is. Its gravity will render this unpredictable in a fraction of a second. So even in principle, intention can't screen out gravity. It's not true that. Well, it's not that it's incompatible with physics as we know it. Even classics.
We better get on with it.
Yep. Thank you, Michael. Okay. Now, where the Hamiltonian view originally came from, in essence, was from the solar system, and the solar system, well, to a fairly good approximation, undergoes time-reversible Hamiltonian dynamics, allowing exquisite prediction. Well, that is, if you consider the solar system for a small enough time scale, if you do it for a long enough time scale, it isn't. But on a short enough time scale, it is, and that we can predict eclipses and all the rest of it. But this kind of motion is the exception rather than the rule. It allows very accurate predictions for the future for a limited time, and the past in this specific, almost frictionless case for a limited time, and that's highly exceptional. Classical physics in the real world is not Hamiltonian. Look, as I say, at macro scales, dissipation takes place. So you've got different levels of description, and if you describe it at the macroscopic level, almost never does a Hamiltonian description apply at the macro level. Is it reversible at the micro scale, but not at the macro scale? The apparent flow of time is just a result of coarse graining and hence an illusion. That's one viewpoint. And my view is that no, complex systems really undergo time change at the macro scale, and actually also at the micro scales. And that is because I believe collapse of the wave function takes place as a real physical process which is also time irreversible. And I'll talk about that later. So Eddington, one of my heroes, puts it this way: the second law of thermodynamics, entropy, randomness always increases. And many of you will know this quote. If someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. If it is found to be contradicted by observations, well, those experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. Okay, now I want to emphasize particularly here something which isn't so much emphasized, but it's the experience of time. The processes in a conscious action. And neurons and synapses operate by spikes, trains going down, triggering activation, thresholds and so on. And the question is, for anybody who wants to say that things are reversible or that the flow of time doesn't take place, the question is, how do we experience the flow of time? And you have to decide, you have to make a decision. Do I believe present-day neuroscience or do I not believe present-day neuroscience? If you believe present-day neuroscience, what happens in the mind is based in what happens in the brain, and that's based in spike trains going down. You've got signals propagating down and going across a synapse through the neuron through to the next one and on, and at a synapse addition takes places and then it spreads out to the other ones and so on. Now, experience of time is based in the physical process. Now, is it only possible that time passes? If you have a theory with time doesn't pass, it isn't possible for these actions to take place in the brain. Time doesn't pass. The brain is a static system with nothing happening. And so if you're going to say that what I experience is based in the brain with most of the sciences believe nowadays, you have to say time passes, because otherwise you can't take the processes that place which will allow me to experience passage of time. Our experience of passage of time is based on ongoing processes, only possible because this was not the case when you think. And so this is based in the Hodgkin-Huxley equation. And at a physical level, it's based in the fact that inside the cell, you've got a cell wall, you've got a extracellular medium, intracellular set of equations. Molecules. These channels are biomolecules. This is a side view. And they let sodium, potassium through that sodium there, and it's there. If the voltage is above a certain level and they don't go through below a certain level, they little micro switches. And that's the basis on which the logic takes place by which the brain works. And the process is that these things diffuse through, and they're allowed through if the voltage allows them through, and they're not allowed through if the underlying physical process underlies our thought patterns.
These molecules exist in many other creatures and living things than us, and some of them you might be reluctant to ascribe consciousness to. So I'm slightly puzzled that you link consciousness with it. I'm not saying that these are sufficient for consciousness. I'm saying these are necessary for consciousness. But it's not. I don't know how. In what sense you can say. You probably can. In what sense you can say well, experiencing the passage of time or a tree.
It might be needed for a longer discussion.
Yep. All I'm going to say is, for our experience of time, it's necessary that these exist. And we can have a long discussion over that. Okay, so I think we've got to take time seriously. In order to do that, we're going to have to move from the commonly accepted view of a so-called block universe to an evolving block space-time. And to start this off, I'm going to say, consider a massive object with two computer-controlled rocket engines that move it left and right. So you've got a huge, massive rock out there in space, a rocket engine facing that way, a rocket engine facing that way, and a computer in the middle that fires this one or that one. Now, you let the computer determine the outcome on the basis of measurement of decay products of excited atoms. So it's like shredding a cat. You've got excited atoms there, and when a detection takes place, it'll move that way, and then the next time it'll take place, it'll move the other way. And the point about this, of course, is the outcome is unpredictable in principle, if you believe quantum mechanics. And there's an extraordinary number of people who in some sense do not believe this, which we can discuss later on, but I'm taking the standard interpretation of quantum mechanics as I have it, that the emission of these particles by this excited atom is unpredictable even in principle. If the object is massive enough, it's moving this way or that way, it curves space-time. And so the future space-time structure is not determinable or predictable from the current data, even in principle. And so this is a Gedanken experiment which I claim establishes that in these circumstances that is true. In some sense that's what the Bohr-Einstein debate was about, but I'm not going to go into the details of that. So this is a space-time picture. This is your past line. At this moment you're at this instant here, and you have this possible path, this possible path, this possible path. These are all possible future paths. Okay, a little bit later, you didn't take that path, you didn't take that path, you didn't take that path, you took that path. And so your path through space-time was that to that. Now you have this possible path, that possible path, that possible path, and so on. And so these are events that have occurred on this side. At a later time, these are events that have occurred. These are possible events in the future. These are possible events in the future here, and these are possible events that did not occur. It's a bit difficult to see the difference between them. And so the present instant is where there is a change from uncertainty to certainty. You don't know what's going to happen there. You do know what's happened in the past. The present is where the indefinite future changes to the determined past. That's the picture that I'm putting. So the evolving block universe grows with time. The past has been determined and is fixed. The future is uncertain and still has to be fixed. Because of quantum uncertainty, it is not true that the future is determined in the present. The present is where the change takes place. It separates them. The future does not exist in the same sense as the past or the present because it isn't yet determined. The determinate region grows with time and space-time itself is growing. As I say, Einstein equations hold. What is different now is the context. So the evolving block universe, at one instant it's like that, next instant it's like that, next instant it's like that, and so on. It is growing with time.
One quick question. What about the notion of it looks awfully like it.
So space-time grows with time, and the crucial difference between the future, and the past. So, if you had a series of pictures of a unique way. If you're given a set of photographs scrambled up, and you've got to find out in which order do they occur. So, as I say, general relativity is completely holding here. It's just that I'm saying in the space-time, what are the boundaries of the space-time? And this space-time has got a fixed past but a growing future. So the evolving the Einstein field equations hold with the boundary specified. The past is fixed.
There's more of it as time progresses.
Well,
the future gets smaller and the past gets bigger.
Sorry.
Semantic, I know, but
What I meant is the past boundary does not change. The future boundary is changing and the past boundary is not changing. Okay, so the issue, Julian's issue, the primary problem is the claimed unique status of the present in the EBU, the surface where the indeterminate futures change to the definite past at any instant. And people come back at me, and probably you're thinking that it's a fundamental feature of special relativity that simultaneity is not uniquely defined. It depends on the state of motion of the observer. What is past and future elsewhere depends on one's motion. For different observers at an event P, different motions will designate different events Q on a distant world line L is simultaneous with P. Hence, the block universe model, the standard one, which doesn't have this boundary, is natural. It's the only way the space-time model can incorporate this lack of well-defined surfaces of instantaneity. Hence, time is an illusion. That's the argument which is made. I think that's what you were thinking of. Now, I have news. Special relativity does not determine the structure of space-time. General relativity does, and you made that point yourself. And so, in fact, you said effectively what I'm going to say now. So the block universe time sections move on, but they are, there's a misprint there. So on this view, they're arbitrary depending on the observer's motion, and someone who is moving differently would have this simultaneity instead of that. Now, the resolution is an interesting one, and something which I only learned relatively recently, having taught relativity for decades. Physically, things happen along time-like world lines rather than on space-like surfaces. And so as far as the determination time is concerned, what I'm going to say is you start at the beginning of the universe, where you've got this fixed boundary at the start in conformal time. You measure proper time along fundamental world lines from the start, thereby determining the transition surfaces, the present, as time evolves along preferred fundamental world lines. So in all of cosmology, there are preferred fundamental lines. Just a minute. You start at the bottom of the universe down there, and you've got these preferred world lines. You measure proper time along these preferred world lines, and that then defines you a surface. And that is the way I'm going to define my surfaces of change. So start at the beginning of time, measure proper time along fundamental world lines, thereby determining the transition surface of the present as time evolves. This is not globally coordinated by some non-local mechanism. It happens locally everywhere. So there isn't some local coordination. What happens is you take each world line and you work on each world line proper time, you measure proper time, it's one of the fundamentals of general relativity, that ends up with a set of points which are all the same proper time from the beginning, and that then is a surface of constant time in this model.
So what do you mean by it? You just said it doesn't need to be a surface.
Well, it'll be continuous. It'll be continuous unless the world lines intersect, which leads to other problems. That leads to a singularity. Okay, so change happens on preferred surfaces of change that are secondary to time, that are secondary in the sense they are derived from time-like world lines. So what I'm saying is the fundamental thing is the time-like world lines, and these surfaces are secondary in the sense they're derived from the time-like world lines. These surfaces need not be simultaneous in the usual sense. Simultaneity is usually determined by radar, is in fact irrelevant to physical causation. And this is the thing, I've taught many courses in special relativity when I've gone through all of that stuff about simultaneity and it's dependent on motion and so on. Actually, that's purely a psychological discussion. It has no physical content. And let me illustrate this. So here is the world line of the Earth, and there's the world line on Mars, and we send a thing over there that's traveling along the surface of Mars, and at event E1 we send a signal to that thing that's sitting on the surface of Mars, and it takes 4 minutes or whatever it is to go over to Mars. It's received over there by this thing, which then reacts to it and sends a signal back, which is received up there. So the physical event on the Earth, you send a signal to this thing on the surface of Mars, it sends a signal back, you receive it up there. You say to yourself, what you say to yourself is, wow, it traveled at the speed of light, it traveled back at the speed of light, it was received simultaneous with this event here. That's what you say to yourself. So you say it took 4 minutes, so 4 minutes after I sent it, that is the instant when it was received over there. Now actually, that's a purely psychological construct. It has no physical outcomes of any kind. It doesn't matter when you think it was received. What matters is when it was sent, it was received over there, and when it was received here. It doesn't matter physically at what time you think is simultaneous here. So what matters physically is E1, the emission, E2, the interaction, and E3, the reception. And what you think is simultaneous with E2 is no physical. So it's purely it makes you feel good to feel it was received at this instant, but it doesn't affect any physical outcomes. And so the surfaces of instantaneity actually are irrelevant for the physics. So what really matters is determined by the metric tensor form of general root, and by the metric on these world lines. So natural.
This incorporates things like world lines separated.
I'll come to that in just half a minute.
These fundamental world lines, some kind of background structure.
Yeah. Yes. Well, in the real universe, there is no vacuum anywhere in the real universe. So the vacuums are a fictitious thing. So I'm coming to that in just half a minute. So natural surface constant time are given by this integral since the start of the universe. Thus we can propose that the present, the ever-changing surface is space-time. If the universe existed forever, we would have to start at some arbitrarily chosen initial surface, but let's think that it had a start. Okay, now is this well-defined world line? And again the answer is we don't live in the flat relativity. The second fundamental feature is that it generally describes the structure of space. The gravity governs space-time curvature. Because there's inter alia, because cosmic background radiation permeates the solar system, all of interstellar and intergalactic space, space-time is nowhere flat or even of constant curvature. So by the way, all of that stuff about de Sitter space-time is an approximation which does not describe actually the real universe. Therefore, there are preferred time-like lines everywhere in any realistic space-time. The special relativity argument, again, does not apply. So what are those world lines? A unique determined choice world lines are the set of time-like eigenlines of the Ricci tensor. An averaging scale, this is one of the fundamental things which choose an averaging scale and are some kinds of matter in principle which don't have a unique time-like eigenvector. Those are not realistic model of matter. So if you like, my definition of realistic matter will be it has of energy conditions standard matter obey. So therefore the formula like because it's true for the matter stress tensor by the Einstein equation, it'll be true for the Ricci tensor, and the equivalence following from the Einstein equation. So therefore we can propose fundamental world lines. The proper time integral used to define the present is taken along the world lines with full velocity u satisfying that equation. Now this will give the usual surfaces of constant time in the standard Friedmann-Lemaitre-Robertson-Walker cosmologies.
You're saying that because of low-order homogeneities, basically, there is no such thing as Ricci flat. Yeah. Right? But then you're using this in the cosmological context, which... Huh?
No, Ricci flat is
I know. But it makes averaging...
You've got to choose an averaging scale. It's the same for every cosmological scale. This is a unique description. The issue that does arise is if I do this with different averaging scales, I will get slightly different surfaces. How do they relate to each other? And that is something one would have to think about. Yeah.
Are these used going to be geodesics?
Sorry?
Are they geodesic?
No, not necessarily. No. They will be geodesic if and only if there's no pressure. So, yeah, the differences will occur at the micro time scale. Yes, yes. So I agree. There's a research program to do to think about that in proper depth.
But that's exactly related to my question, because I think that assumption about the Ricci applies at the micro scale, but then you are just considering differences at the micro scale.
Yeah, well, every single model in general relativity always has an implicit averaging scale in it, and we usually deal with it only at one average scale. Very, very seldom do we consider the relation between different averaging scales. I happen to know that because I spent a lot of time thinking about that. Now, there are 2 points about this. So this is the picture. The evolving lock. The present is where the future change of the past takes place at long preferred time, like world lines. The average, and this is the average motion of matter. It's the Landau frame, which is the average motion of matter in the universe. And in cosmological perturbation studies, this is the unique frame which is defined by the matter in the universe. It's not? Yes. What about simultaneity? In general, these surfaces are not related to simultaneity as determined by radar. So there's no reason whatever in a general Robertson-Walker model, but in a rotating model, they won't be simultaneous. Indeed, this is even so in the Robertson-Walker spacetime. Interesting feature of Robertson-Walker spacetimes, which perhaps you haven't thought about, that in a determined where the radar definition is simultaneous of static.
But they are simultaneous in the sense that they are always space-like separated.
Space-like separated.
I mean, if you were to count the distance, if the metric distance between two of them, they would always be space-like separated, not causally related.
These surfaces need not necessarily even be space-like. And that will depend on the inhomogeneity, the anisotropy. In a Robertson-Walker model, they are space-like. In a Bianchi model, they will be space-like. In a very perturbed universe, maybe or maybe not. But to return to something which was implicit in what some other people's, what happens if these world lines intersect? And the answer is because they're the Ricci eigenlines, if they were to intersect, the density would diverge and there would be a space-time singularity. And so that would be the end of that. And so if they were to intersect, this would be where matter was diverging, and the Ricci the Ricci tensor scalar would diverge there because of the timeline. This now depends on your averaging scale. Yeah. Yeah. Okay. What will? Yes. Yes. Okay, what will have to happen here will be something like, it's not, I haven't got a full answer to this, but something like this must be worked out, that at the large scale, where the gravity is taking place, you'll have to do an averaging because gravity is a long-range force, which, yep. Okay. A key question some people have asked is how fast does time pass? But Paul Davies, Bernard Carr and other people suggest there is no sensible answer to this question. How fast does time pass? I claim that the answer is given by the metric tensor, which determines proper time along a world line by the formula I've already given. This is the time measured along that world line by any perfect clock. Time changes at the rate of 1 second per second, as Tim Maudlin has stated, and what determines it is the metric tensor. That's the function of the metric tensor, is to tell you how time changes relative to any curve parameter that you choose to put. This is what fixes physical time, including gravitational time dilation. Gravitational potential affects the relative rates. Real-world clocks, oscillators that obey the simple harmonic equation, are approximate to such ideal clocks. Again, Julian mentioned this. And it is the relation between such clocks and other physical events that measures the passage of time. One of your problems here is if you have many different clocks, a cesium clock and other kinds of clocks, do they give you the same rate of time? And of course, one of the fundamental features of physics is that it is the same time parameter that occurs in Maxwell's equations, Newton's equations, the Dirac equation, and so on. It's the same time parameter in all of those equations, which is one of the foundational things in physics. The metric equivalence. So if the metric tensor determines proper time, what determines the metric tensor? Well, the Einstein field equations. So we use the ADM representation. The first fundamental form of the first fundamental form, that is, the metric is represented in the standard ADM way with a shift function and a lapse function. You do a 3+1 splitting with time and 3 space coordinates. The lapse function and shift vector represent coordinate choices and can be chosen arbitrarily. G is the metric of the 3 spaces, T is constant. The second fundamental form is the derivative of the normal vector n, where n is the normal vector, and the matter flow lines have a tangent vector which is not the same as that in general. This has got indices downstairs and this has got indices upstairs. And so if ni, the shift vector, is different from 0, these two vectors are not the same vectors. And so in ADM coordinates, you've got your matter flow, you've got your lapse, which is orthogonal to the world line, you've got your shift vector like that. The shift vector gives the change of matter lines relative to the normal to the chosen surface, as the lap function gives the relation between coordinate time and proper time along the normal lines. Given that, the field equation, your two constraint equations, constraint 1 and constraint 2, the three-dimensional Ricci tensor is related to the matter density in that way. The matter flow flux is given in terms of the divergence of the second fundamental form. So those are the two constraint equations, and then there are 12 evolution equations. The rate of change of the metric tensor with the source term given by the second fundamental form, and with the term pi coming in there. Sorry, those are the derivatives of the shift vector, and the source term is a second fundamental form. And how does that evolve? It evolves according to this equation here, and it's determined by the matter tensor, and these are the ADM equations. And then you say, well, have to say, well, what determines how the matter evolves? Well, the equations state for the matter, the equations of state for the matter, together with the conservation equations, determine how the matter evolves, and now you've got the complete set of equations. Okay. We determine the lapse function by the condition that the time parameter measures proper time along the fundamental flow, which is, so you put ds squared minus d tau squared. Equation. Constraints are conserved. The development of space-time with time takes place, as is the case for other fields, with the relevant time parameter being time along the fundamental flow lines. There's no problem with the existence of the rate of flow of time. Time flows at the rate of 1 second per second with determined tensor. And so that is the way that I see it. Okay, now this is probably what I'm going to have to finish with. The there's no basis for such a determinism in microphysics alone that H theorem holds for all quantum field theory applies equally in both directions of time. That's Schrodinger's paradox. So the fundamental microphysics cannot provide a foundation for the second determinism with the unique direction of time on its own. Microphysics is time symmetric, future and past are equal. However, the macrophysics know the direction of time. In the block universe, the standard block universe, we've got the whole time present that is equal. Now, in the evolving block universe, the error of time arises fundamentally because the future does not yet exist. The global asymmetry in the physics context. Time and propagator can only be integrated over the past because the future isn't there, and so when you've got those different fine past one, because there isn't any, you can do the integral. One can be influenced at the present time from many causes lying in our past, as they have already taken place, and their influence can therefore be felt today. One cannot be physically influenced by causes coming from the future if they haven't yet come into being. And this is the rationale for saying the past exists but the future does not. If something can influence you, it exists. And so, for instance, the past exists and is developing to the future, which does not yet exist. Is this asymmetry that leads to the arrow of time? It's not the outcomes. In this room is this is a time t star ago in the past, inside a star that lies inside our physical horizon. These elements you have to have a special condition which a lot of people have written about in order that the second law of thermodynamics agree. This sets what I call the direction of time. The direction of time exists because the future doesn't exist but the past exists. So that's the arrow pointing from the part of space-time which does exist to the part of space-time which doesn't yet exist. So that's the direction of time. The arrow of time is determined locally by local physical events. Yeah, sorry, I haven't got the proper picture for this. And that is where entropy increases. And so the fact that entropy increases, special initial conditions in the early universe is not the same as the direction of time. The direction of time and the arrow of time are decoupled up here. The direction of time comes from space-time growth. Special initial conditions. Even irreversible when wave function projection takes place. That's the core of the flow of time in my the function collapse takes place, and this it does not need to relate to an experiment. So you've got your unitary time evolution. The wave function is where the indeterminate gives way to the determinate past. Unpredictable from past data, and that's where the real dynamics takes place, because quantum physics is not time reversible despite what some of our colleagues say. It is referring only to Hamiltonian dynamics, which is a crucial feature of the theory. And so when a measurement takes place, initially the wave function is a linear combination of eigenfunctions. After it, it's just one. And from here, you cannot predict backwards. There is no possibility, even in principle, to determine what the wave function was before from the data you have at the later time. And so if you look at the micro level, I believe that what causes this going on is the collapse of the wave function. Initial state 1 does not uniquely data, it's due of quantum interactions. You can predict the statistics of what likely to happen, but not the unique actual physical outcome, which unfolds in unpredictable ways as time progresses. You can only find out this outcome after it has happened. And so my hypothesis is that this is where the flow of time takes place. The future changes to the certainty of the past, and this happens all the time, everywhere. Idea, why should the collapse of the wave function relate to the universe? And that's because the collapse of the wave function is contextually dependent. I'm completing a paper about this, trying to make this very clear. Where the wave function depends on local physical circumstances determined by the local physical environment, such as the measurement apparatus or any physical system that causes collapse of the wave function. And so I better stop here. Just quantum gravity will of course have to eventually be the ground for all of this, and spin networks are the kind of picture, I'm not saying particularly that I'm saying spin networks, right, but they've got exactly this kind of picture of a growing block universe. For some reason they put downwards instead of upwards. A picture of a block universe which is growing with time as events happen with time, and so the space-time is actually increasing.
Hello? Is that working?
Oh, just for the okay, so as usual, start with the question. The students for the questions.
Come on, some of the students must have a question.
You say direction of time caused by a collapse of wave function? I mean, the origin of direction of time from the collapse of wave function?
I think that ultimately, what we will need ultimately is a quantum gravity description in which the growth of space-time is an outcome of the collapse of the wave function in quantum gravity. Now, I've never seen anybody writing about the relation of quantum gravity to the idea the collapse of a wave function, but I presume if quantum gravity is a real quantum theory, it must have the idea of collapse of the wave function, and that would have to be related to the idea. This is a discrete version, so let me add one further point about this. I happen to believe also that space-time is discrete, and so this picture here of the spin network picture is very much the kind of thing which I think is the correct viewpoint, that in fact these jumps would, at the micro level you will have discrete jumps where space-time increases, not a continuous, in my view.
So, well, I just wanted to get back to one of the points that you mentioned, that this surface need not be space-like.
Yep.
But then, suppose that 2 points like that are related, are time-like.
Yeah.
Then couldn't it mean that this point could actually, it's not the border of space-time in a way, it's not this, because this point would evolve to the other, which is still in the border.
All right, the thing which I didn't mention is the following. This has one really nice picture which I think you're kind of talking about. If those world lines intersected, you would get a singularity forming, because they are, those would be at the scale. Look, that there is this problem of scale. And if they intersect, a singularity occurs, and so what this does, it solves the chronology protection problem. It prevents the existence of closed time-like world lines, because when you're trying to cause a closed time-like world lines, roughly speaking, the space-time which is coming up this side and the one up that side, they both try to go into the same future space-time. They can't do that, and they form a singularity when they...
Are the eigenvectors always time-like?
Sorry?
So are the eigenvectors of the Ricci always time-like?
Yes, yes. That's my definition of realistic.
That's the definition, okay.
That relates to what people they call shadow matter and all this kind of thing. I don't regard that as physics.
The floor's open for questions, so please put your hand up.
So just to make the one defensive point, I do see that there is an issue about the relation of the macro and the micro scales. My view is one, because of what I started off at the beginning, we've got to be able to relate the fact that we experience time flowing on at the scale at which our brains operate. Our brains are based in physics at the micro level. Time must pass it that way. In order to make sense of that, we have to produce a picture, the picture I've given. And if this one doesn't suit you, then I challenge another one in which it does make sense to say that time actually does evolve and events actually do take place.
I've got Tony and Julian. Put your hand up now if you want to ask a question. I'll put you in the queue. Sure thing.
Okay, so I'm pretty sympathetic to the idea of like measurement being a kind of objective process, and lots of other reasons why I think that's true. But if you accept that, then I'm not sure if you actually need past hypothesis to define the arrow of time, because it doesn't...
You need past hypothesis for the arrow of time, not for the direction of time. The direction of time says that the initial boundary is fixed, the future boundary is moving, the direction of time is the direction in which the future is increasing. The arrow of time is the local statement that entropy increases this way rather than that way. Now, in order that works out, you need the past hypothesis. So you can have the direction of time without the past hypothesis, but you need the special conditions to get the...
So you think that the clocks of the wave function is giving you just the direction of time?
Yes.
And okay.
Yes. Yeah, and it is crucial. Yeah, well, yeah.
I'd just like to ask if you really have to put so much faith in this expression, time passes. Let me finish if I may. This is a comment rather than well, it is a sort of a question, but I'm challenging you. I would say there are just two pieces of evidence for the past that we have. One is that when I move my hand like that, both you and I actually see the motion. The second one is accumulation of our memories. I have very vivid memories of the various times you visited my house, George, and you of me. And that's all in my brain now. I have, so to speak, still very vivid, I close my eyes and have very vivid sort of photographs of you in my mind that I can then compare with seeing you now. Slightly different, and it's that slightly change, as we in the normal way of saying we get older. I don't think there's any need to talk about time at all. We just need to talk about differences and approximate congruence. Your picture now is almost congruent to when you first visited me for the first time in North Oxfordshire. And I don't think we need this talk of time and the idea that time is passing. It's Bergsonian intuition which doesn't really belong in a proper scientific theory.
It depends what you mean by a scientific theory. When you said you can compare them, the act of comparing is an act which takes place in time in your brain. It relies on those neuroscience processes I talked about. Otherwise, your brain cannot compare one thing with another. Comparing is an act which takes place as time passes.
But if I had taken a picture of you 5 years ago in my home and put it on the board there, I could see the picture of you 5 years ago next to you now and see that there's near congruence between them. And I don't think that a passage of time is involved in that comparison.
The fact of seeing involves the passage of time. It involves these propagation of these action potentials from your eyes down to your thalamus and up to your visual cortex. You can't see anything unless time passes.
Sorry, I'm sure we have enough to say, but I feel
Hi, so I just wanted to ask, so I can see that you really want to have this sort of present time that's defined by these preferred world lines, but why do you want to keep the past inside the universe? What, could you just not have an evolving present?
Sorry, I rather rushed through this. My definition of what exists is if what exists is what we see around us in this room. If something can be demonstrated to have a causal effect on what is in this room, then it must be said to exist. Otherwise, you have an effect without a cause. Now, what exists in this room, all of the material in this room was caused by interactions in stars 7 billions of years ago and by primordial nuclear synthesis. That has to exist, otherwise you have things existing today which exist without any cause, and so that's why you have to say that the past exists.
Okay, just what about, do you admit quantum fluctuations of the metric and the Ricci tensor themselves, in the sense that it seems that you require a definite value for them to define this growing block, because they're the ones that define the eigenvectors.
Yeah,
would you be able to accommodate superpositions and all of that?
Okay, I have a whole little further discussion which I haven't given here about the relation of all of this to Wheeler's delayed choice experiment, which is actually quite an interesting kind of little further discussion. That you can find a paper on the archive called The Crystallizing Block Universe, which talks about that. But roughly speaking, what this says is, if you look at the micro level of the surface, it can have little delayed patches where these delayed experiments, like the Wheeler delayed choice experiment, take place. So it's very fluctuating on a very micro kind of level. This would be the kind of idea that I have for that.
Sorry, I didn't understand the answer. How it relates to the superpositions of the metric?
In the Wheeler delayed choice experiment, you can in effect reach back into the past and change things decide whether photons way back there are going to particles or as waves. You know Wheeler's delay?
I know the choice experiment, but I don't understand where it has to
in some sense, in a very, very micro scale, you are reaching way back past, which that means the surface. considered from the quantum viewpoint will have big on in it.
Okay, let's talk later.
Yeah. So anyhow,
Are there any further questions? I have another question, yeah. If you'll be during the opening, I have a question. Go on, oh yeah. Question?
It seems we need to specify initial state as well. The whole thing. So how do you?
yeah, you have to just specify the initial state. The problem will be if the universe is singular, how do you specify a singular initial state? Yeah. So that doesn't change. But what is fixed is that the universe. That initial surface is fixed and doesn't change. The future one is changing all the time, and I'm prepared to defend that quite strongly.
On that note, shall we?
It's hot in here. Do we want 2 minutes break? Yeah. Okay. Okay. Yeah, why don't you do it, Green?
Just start again in a couple of minutes.